Well, I just started recording. Okay, where's my... Oh, I forgot. It's not connected yet. Okay. Yeah, well, you have to do it safely, remember. Okay, finally we have recording started. All right, so we got about 4 weeks left, thereabout. So what we'll be doing is we're going to finish up, all the topics, with subroutines, and basically how to convert C code into assembly code. So we'll deal with pointers, we'll deal with arrays, we'll deal with local variables, parameters, dereferencing, and that sort of thing. The only thing we're not gonna touch, unfortunately, I wish we could, are structures. Okay, so structures, I can't really do it because I don't have the infrastructure in the toy processor tool chain to really effectively do it. I can talk about the concept, but I can't really do it because there's not enough code space to actually deal with structures. So that's the only thing that I cannot deal with. Yeah, because we only got 256 locations for both the stack and also the code. So that's can't really do a whole lot with that, but enough to illustrate concepts. So what we'll do today, and I'm just double checking to make sure that we are in fact recording. Yep, is to talk about subroutines. I think we already talked about how to return a value from a subroutine, a scalar value. So anything that's an integer, a pointer, that sort of thing, we use a register so that this called subroutine can set the register to the return value, and then the subroutine that the caller can then pick it up from the register. It is an agreement, okay? So everything between a caller and the subroutine being called is done by agreements, okay? It's basically a set of standards. You can basically say that each compiler can have its own standard. As long as it is consistent between the caller and the callee, they will be able to find the parameters, they will be able to find the return values, and so on and so forth. But the interesting thing is most compilers actually conform to the same standard. When you have common architectures like the i386 or the AMD 64 architectures, which are the two most common desktop architectures, not counting servers, because servers are actually mostly running ARM or PowerPC type of architectures. All right. So what we'll do is, today is I'm going to write a lot of sample programs. Okay, I'll write the program in C on one hand, and then write the same code in assembly on the other hand. So this way you get to see and compare, how it works out. Okay. So we're not going to focus on control structures anymore. That's kind of the topic from the past. So we'll focus on, how a caller and a callee talk to each other. So that's going to be our focus at this point. All right. So given that, let's go ahead and talk about, we talked about return values already. So the next thing we can talk about are parameters. In other words, let's say I have a subroutine that's like this, okay? This is f. It has got two integer variables, x and y. And the only thing it's going to return is x plus y. Okay? Obviously, function f is not a particularly useful function from the perspective of C programming, but it serves the purpose of discussing how do we pass parameters and how do we access the parameters inside a subroutine. So we'll look at things from the perspective of the caller, we'll look at things from the perspective of the called subroutine, and then we'll work out all the details. So in this case, we have main as a function. So in C and C++, main is basically just a regular function. It's not any more special than any of the other functions, other than this is the entry point of the entire program. So other than that, main is not special at all. So in here, I'm just going to call f, okay? In fact, I'll even have my own local variable, so we can illustrate that concept later too. So we have x as a local variable. Let's call it something else. Let's call it n, so that when we talk about n, x, y, they're distinct in this particular program. So we can say n equals to f of 2 and 3. And that's the end of this entire program. So this program will compile in C. In fact, we want to compile this program in C just to kind of check out the addresses of n, x, and y and see how they relate to each other, because there's a certain relationship between those three variables or constructs in this particular program. First thing first, is n a global variable or is it a local variable? It's a local variable. If you're given the choice, you can do it in either way. Would you choose a global variable or would you choose a local variable? Local. And why is that? Keep track of your data better when you first start. Okay, so that you cannot have side effects. Now, side effect, refers to routine changing something that is not passed as a parameter into the subroutine. Now, global variables, as the name implies, is global. Everybody gets to see them. Everybody gets to change them. So if you rely on global variables, to communicate between the subroutines, if one subroutine is misbehaving and changing the global variable either unexpectedly or incorrectly, it's really hard to track down who is responsible because everybody has access to it. It's kind of like, you're going to a, like a lunchroom, okay? And you have a coffee mug that everybody can use. Okay? Every single time you walk into the lunchroom, it's dirty. Who did it? That's your global variable. Your local variable, on the other hand, is the one that you keep in your backpack. Okay? You drink, but when you're done, you keep it in your backpack. You're the only one with access to it. So if it's dirty, guess who's responsible? You're responsible. Someone else. You can always try to blame it on somebody else, but it's really hard with local variables. Now you can, okay, if you pass a local variable by reference, or if you pass the address to a subroutine, then a subroutine has a way to find the local variable and change it. But guess what? You left a trail of, yes, here's where to find my coffee mug. If you need it, go get it. So you can actually track it down by looking at the function call itself to say that, yeah, I guess that guy has access to this particular local variable of mine, and as a result, it might change that, okay? But this is also why const is useful, because when you use the word const in the right context, in the right way, you're telling the compiler, hey, the subroutine is not supposed to change this, okay? So if the subroutine is implemented to change it somehow, the compiler will warn and go like, hey, you're not supposed to change it, it's a const. That's what the word const is really supposed to be used. It doesn't really do anything as far as the code is concerned. It is really a check that is done by the compiler so that you can say, hey, the subroutine is not supposed to change what this point is pointing at, and it will be enforced by the compiler. Okay, so we look at this program, and we'll go ahead and actually compile it. So we'll save the file. Okay, we'll save it as, let's call that simple.c, because it's really quite simple. And we go to a, where's my big command line? There we go. Okay, so we do a gcc-g-1 all. The name is what? Simple.c. And it warns me about one thing. It says, variable n, which is the only variable in the entire program, which is a local variable in main, is set, which means it is changed or written to, but not used. In this context, used means it is read. Okay, it is utilized in some other calculation. So it can potentially be a warning, because if you have a typo and you name a variable in a particular way, but then you do not end up accessing it, it could be a typo issue. So that's why the compiler warns me about it and go like, hey, you put something into n, but you never really use it. Okay, It's a potential problem. It's not a problem itself, but it is an indicator that I might have a problem. So now I use GDB to look at main, a.out, and then we list the program, put a breakpoint on, I can put a breakpoint on line 9, okay, the first line that is kind of interesting. So then we run the program, now we are on line 9. I'm not really interested in n right now, I'm interested in the address of n. Okay, so we print the address of n, okay, it's something. We single step, now we're in the subroutine. So when we're in the subroutine, we can say, okay, tell me what is the address of x, and tell me what is the address of y. So what do you notice about these three addresses? The actual distance between them is not the key. It is the direction, okay? You know, it's increasing order, decreasing order, that sort of thing. So what do you notice? Decreasing order, very good. So you can see how local variable n of main has the highest address of these three, and then the two parameters, x and y, has the lower address. You can also see how the second parameter, which is y, has a higher address than the first parameter, which is x. So that is kind of interesting because it tells you how the caller is communicating with the callee. Because ultimately, who is x and y on the stack? Is it the caller or the callee? The caller, right? The caller is the one responsible to put it on the stack. The callee is really just saying, oh, I need to use x. Where is it? It's over here. Oh, I need to use y. Where is it? It's over here. So the callee is really just using the value of the parameter, but it is the caller who puts it there. Okay? But you can also see there's a lot of stuff in between because BC and 9C, there's a lot of bytes in between. So the compiler is actually generating a lot of code to keep track of more than just local variables and parameters on the stack. We know for sure there's the return address on the stack. In other words, at the end of the execution of a subroutine, how does it know where to go back to? That's because the caller, before transferring control or continuing execution in the subroutine, put a little piece of breadcrumb on the stack and say, okay, subroutine, when you're done, this is the address, so they can go back to it. So that is on the stack as well. All right, so this is kind of interesting. So now what we want to do is we want to replicate this program, but in assembly. So let me go back to here, and we'll open a new file to implement the assembly code. So this way we have the C implementation all by itself, and then we have the assembly implementation also all by itself. Okay, so here's the assembly implementation on the side. So the assembly instruction is, well, I usually just start with main, because when you reset the processor, the program counter is always reset to 0. Okay, some car alarm is beeping. At least make it musical, right? I mean, or at least make it imitate screaming of some kind, or baby crying, that sort of thing.
I make it so much more pleasant.
Or cats on fire. No, I didn't say that. No, I didn't say that because I have 2 cats too. I certainly do not want them to be on fire. At least not when they are alive. Okay, so main is the entry point of the program. In a C program, there's actually quite a bit of code before your main actually gets control. So you don't really have any control over that code. It's the initialization of the entire program space. So by the time it gets to main, a bit of code has executed already. In the toy processor, on the other hand, there's no operating system, there's no loader, there's no library code that runs before your code gets control. So your code really starts at location 0. So main has to be the first thing in the entire program. Is that okay? Now, obviously, I don't really need a label for main because it starts at location 0 anyway. I don't really need a label to say, hey, this is the entry point of the entire program. This is really more or less for documentation purposes. Okay, so I just want to indicate that, okay, this is the entry point for what we knew as main in C and C++ programming, but in assembly, it simply is just a label to say that this is the entry point. All right, so the first thing we need to do, because we don't have the code that goes before this, it is not necessary, but we kind of need to talk about it. So we need to initialize the stack pointer. Initialize the stack pointer. And I initialize the stack pointer to 0 because subtracting D from D would end up with a 0. And storing that back to D means I'm just making sure that D, register D starts with a value of 0. But 0 is also known as 256. It's just that we only have 8 bits. We cannot store 256. That is the one location that is after the end of the entire memory space, which is the stack pointer. What the stack pointer should be pointing to, because that's the one location that's supposed to be the last thing pushed on stack. But we don't have anything on stack, so that becomes what initial value of the stack pointer. Okay, that's the only thing that we need to do as far as initialization is concerned. So now we need to look at the C program. We have a local variable n. And the local variable n is going on the stack. In other words, if you have a recursive subroutine, every single time you have a recursion, every time you have an invocation, each invocation has its own copy of that local variable. That is why recursion works. Without having each invocation having its own copy of a local variable, recursion would not work. Is that okay? So we'll talk about recursion when it's time to do it. But right now, we'll just do a decrement D to allocate space for local variable n. So this decrement D is really just saying, I'm going to reserve a byte for local variable D. So that means register D is decrementing from 0 down to 255. Now, the stack pointer always points to the last thing that it was allocating for, or last thing that it stores. So right now, it is pointing at local variable n of main. So local variable n of main has an address of 255 in decimal, or FF in hexadecimal. Okay, very good. And I'm just doing a line-by-line translation from C. I could have done something a little bit differently, but I'm just going to do it based on the C code here. All right, so the next thing we need to do is what? Do we need to worry about where to find n, or do we need to worry about calling f first? Which one has to come first? This is the confusing part, because in most languages, especially Western languages, we read from left to right, right? So we kind of have that kind of implicit order of whatever is to the left is what we need to think about first. But in an assignment statement, it is actually the opposite way. Okay, we have to evaluate what we call the right-hand side of an assignment first, because that's producing a value that we can store. Once you have the value to be stored, then you look at the left-hand side, go like, where are we storing it? So that's why when we get to the line of n equals to f23, we worry about the right-hand side first. How do we call f so that it can return a value that we can store into n? Is that okay? So I'm not even concerned about, oh, where do I find n at this point? I'm just focusing on how do we call f? How do we make sure that f has the two arguments that it needs? 3 is the second one, and 2 is the first one. Is that okay? So the next thing we need to do here is to push the arguments on the stack. But when you push arguments on the stack, it has to be the last argument pushed first, because we have to make sure that the second argument or the last argument has the highest address, and then the first argument has the lowest address. And that's why the last argument is pushed first. So that would involve LDI A3, because that's argument. The second argument has a value of 3. Okay. Decrement D, and then we have a ST instruction to store to what D or the stack point is pointing to, and A contains the value that we are storing. So these 3 instructions together is what we call a push operation. We're basically pushing a constant of 3 on the stack as the second argument. Is that okay? Are we doing okay so far? So we're only looking at things from the perspective of the caller and go like, okay, this is how we supply the arguments on the stack. So the next thing we need to do is about the same, except it is a 2 this time, because we are trying to push the first argument. We have the decrement D again, because we need to allocate the space first before we store something into that space that we just allocated. So these 3 instructions together is push 2, which is basically putting the first argument on the stack. Are we doing okay so far with all this stuff? Okay. Once we have all the arguments on the stack, the next thing, the last thing we need to push on the stack is the return address. In other words, we have to let the subroutine know when it's done, you need to get back to right here. Okay, so I'm going to put a label down here first, main return from F here. Okay, so I'm just making the label kind of long, but it kind of self-documents what it is. So we have LDIA main underscore return from F. Decrement D, because we always have to allocate a space before we store, because otherwise we'll be overwriting something, something that already has a meaning on the stack. So then we have a store instruction here to store whatever A has. So you can see how I'm using A as a scratch register for the most part. Okay, it's not particularly useful. It's just that our limited instruction set can only store something in a memory location once that something is in the register. So that's why we need to put in the register A first. Okay, so the next thing we need to do is to JMP_I, jump I or jump immediate to the subroutine. So jump I to F is not really that mysterious. All it's doing is to say, okay, now that we have set up everything on the stack, it's time to continue execution in the subroutine. That's all it's saying. Okay, so assuming it's going to magically get everything done with 2 plus 3 stored in register A, because that's the agreement. So we can now assume register A has the return value. We can also assume the return address is popped. In other words, it is utilized and the stack has already cleared that particular location. That is the agreement. Okay, once again, this is a convention. The convention is to assume the subroutine is responsible to deallocate the space used by the return address. Are we doing okay so far? Can we all distinguish between what is a return value versus a return address? A return value is a C concept. Okay, whatever you put next to the return keyword is the return value. The return address, on the other hand, is not really visible from a C program's perspective. We know it has to exist because when you execute a return statement in C, somehow, magically, it knows where to get back to the caller. That's the return address doing its job. Okay? All right. So after these 2 assumptions, what about the 2 and the 3? The subroutine says, not my responsibility. So the caller has to clean that up. So now the caller has to clean up those 2 locations by incrementing D. So the first one is to clean up after the first argument to F. Then we have to increment one more time to clean up after the second argument to F.
And so in this example, the first argument sent to F would be 2?
Yes.
Okay.
And then the second one is 3. Yep. Huh? The first argument is 2, the second argument is 3. But when you're pushing, you're pushing 3 first, and then the 2. When you are cleaning up, you're cleaning up the 2 and then the 3 because of the last in, first out. Yep. Okay, so now we finally get the stack to quote-unquote balance because it is back to the point right before we perform the function call. So can someone what D is pointing at right now? It's pointing to n. It's pointing to the local variable n. How convenient, because the return value is supposed to be stored in n. Okay, So all we need to do, okay, so let me just emphasize here, D points to N right now because we balanced the stack. Okay, whatever we push for the arguments is no longer needed at this point, and we deallocate all those bytes. So that's why it is back to the point before the function call. But that's really neat because all we need to do now is to say store to whatever D points to with the value of A. What is the significance of A again? I mean, it's on the projector already. That's the return value. So it's very convenient right now because register A is the agreed register to contain the return value from the called subroutine. And register D, the stack pointer, just so happens to point back to the variable that I want to store to. So a single ST instruction gets the job done. Are we doing okay so far with this code?
And so after this, we have to deallocate the space for the in, right?
Correct. So if you are looking at main as if it is a real function, then you have to deallocate for the local variable. So now you have to do another increment D to clean up after the local variable n. And then we're supposed to return here, but since this is the in assembly code, there's nothing to return to, because in a C program you return, and then it will basically exit the program. You go back to the command prompt, or you go back to code blocks or whatever. But the toy processor has nothing to return to, so the only way that makes sense to end the program is a halt instruction. Yes, go ahead.
So right now we haven't actually touched the intf function. We're just talking about the
That is correct.
Okay.
We are implementing just main at this point. So main translates to this code.
Okay. And the code block after the main return is basically pretty much after the n equals or like right from that point onwards.
Yes, if I were to point out, which part is which part, this is sort of, okay? Int n is sort of this one here. This code here, calling f with 2 and 3 as parameters, and also the call and also the cleanup, is basically going from here all the way down to here. That is f of 2, 3. It sets up the parameters or arguments. Okay, when you look at it from the caller's perspective, they're called arguments. When you look at it from the perspective of the called subroutine, they're called parameters. So it sets up the arguments, it sets up the return address, it continues execution in the subroutine, and then it cleans up the arguments which are no longer needed on the stack. So this entire chunk of code is really just doing f of 2, 3. Then it comes the part to utilize the value that we have in register A, which is the return value. So I can actually do a slightly better job here. So this part, oops, okay, touch something I'm not supposed to. There we go. So this part translates to the utilization of register A and storing into a local variable n, and that's just that. And then this part is invisible from C. There's no actual visible code because all we are doing is cleaning up after everything. That's the local variable. And then the halt is replacing a return 0 because we have nowhere to return to. So the best thing we can do is just to say, okay, we're done. Okay, execute a halt instruction. So are we doing okay? This is all good? Okay. Cool. Shall we move on to the implementation of the subroutine itself?
Yeah, where would we put it? Would it be underneath this or would it be above it?
You want to put it below, because if you put it above, then when you start the execution of the program, you'll be executing the called subroutine instead of main. Yep. So it's kind of, you have to adjust for that. So now we are looking at function f. Now, the typical way that I look at this is I would write comments to say what is on the stack so that I have a frame of reference to know, okay, what do I expect at this point? So I would just write it like this. Y should be on the stack with a higher address. X should be on the stack with a lower address. Then we have the return address on the stack, which is even lower than X. Now, because in this case, I do not have any local variables, I'm not going to say anything here. If I do have local variables, it would go below the return address. Because everything up to this point, y, x, and the return address, they were all set up by the caller. I don't even have a say of how these things should be ordered on the stack. It is an agreement that the caller will give me these things in this particular order on the stack. Y has the highest address, followed by x with a lower address, and then followed by the return address, which has the lowest address. And guess what? One thing that I also need to point out is that the stack pointer is pointing to the very last thing that was pushed on the stack, and that turns out to be the return address. So this is what the stack would look like at this point. We have the 2 arguments on the stack and the return address, and then the stack pointer is pointing to the return address. So when I get here, I look at the C code and go like, okay, we need to get to x, we need to get to y, then we need to do the add, and then return it. Okay? So the first thing we need to do is to go get y, okay, or go get x. You can either get x first or get y first, because addition is commutative, which means you can switch the order. It doesn't really change the meaning or the result of the addition. So I can do it in either way. But I'm going to follow the code from left to right, so we are going to use get x first. Do we have anything that is conveniently pointing to x right now? No, the stack pointer points to 1 byte below where x is supposed to be. Now, this is very tempting, okay? So most of you go like, well, we can just do this. Then D is now pointing to x and everything is cool. Well, this is where it's difficult to explain without explaining interrupts first. So I'm going to spend the next maybe 10 minutes or so to explain what is an interrupt and why you do not want to change the stack pointer itself to access something that is above what the stack pointer is pointing to. Okay? An interrupt is a concept in hardware that the toy processor does not emulate. Okay, so there's no way you can actually run a processor and understand what an interrupt is. So the best way to describe an interrupt is to describe what you need to do without interrupts first. Okay? So imagine I'm the processor, okay? And I am dealing with a DOS prompt, okay, or a Linux prompt, or whatever command line interface that you're dealing with. So if you think about the command line interface, what does it need to do? For the most part, it just sits around doing nothing, right? It doesn't have anything to do until you type something on the keyboard. Is that making sense? Okay, let me give you an example. Okay, this is a command prompt or command line interface, and I'm going to exit, get out of GDB. So this is the shell. Okay, this is the command line interface. What do you think this program is doing right now? It's waiting for me to type something on the keyboard, right? Okay. So there are 2 approaches. Without interrupts, then this program has to do what we call polling. In other words, this program, command line interface, will keep asking the question, are you typing something? No. 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 And it will keep asking the question. And until I actually type something, it'll keep asking that question. And it's actually asking that question as frequently as it possibly can. So with a Pentium, not Pentium, i7 processor running at 3 gigahertz, I'm assuming it'll be asking that question at least millions of times per second. How fast can you type? And guess what? It's also using a lot of energy, because when it's actively executing code, it's going to consume energy. So your 95-watt thermal output of the processor is mostly spent asking that question. Did you just type something on the keyboard? Which is not a very good use of processing resources, unless your room is really cold and you want to turn your computer into a heater. Is that making any sense? Okay. So polling is not a very good way to do things. We used to do that. Okay. If you look into DOS, like the real DOS back in the IBM PC days. Okay. if you look at CPM, if you look at all of those simpler operating systems, they all do polling because guess what? It's easy to do, for one thing, and they don't really have anything else to do. Because a DOS program is a single program, single thread, single process. There's only one thing it can do at any time. There's nothing to do otherwise. So it can afford to do polling. Your PC, on the other hand, has got lots of stuff happening in the background, especially if you run Windows. At any time, it could be updating it, which takes a lot of resources. So if your command line interface is taking all the resources, then it has no resources left to update itself, okay, or to do anything else. So that's why polling is not a very good idea. So instead of polling, most newer operating systems would use interrupts, which means the operating system, it will go like, I got nothing to do at this point. Okay, there's no key press, I got nothing to do. So this particular program, this particular thread, I should say, will execute what is equivalent to a halt instruction, which means it enters the execution phase of that instruction and doesn't get out. Now the halt instruction also has a very special effect. It consumes no energy, almost no energy to execute. So when you only have one process and one thread, and it wants to execute a halt instruction, your processor power consumption goes this much because it doesn't need to do anything. It turns off most of the changes. It will still be clocking, but all of the registers, all of the ALUs, all of those multiplexers and demultiplexers, they're not doing a single thing. It is only when you have a state change that it consumes energy. So when there's no state change, the processor doesn't really use a lot of energy. So that's how your laptop computer can extend its life, is by executing the halt instruction as much as it possibly can. Is that okay? Okay. So the computer or the program is executing a halt instruction, which in theory there's no way to get out of, right? At least in our case. So then you type something on the keyboard, or something happens, okay? Then what happens? What do we do now? Interrupts. Okay, so an interrupt is basically a hardware way of saying, hey, processor, something just happened. I need you to do something about it. Is that concept okay? So it's kind of equivalent to in the lab, okay? In the lab, you guys are all doing your stuff, right? So unless you guys have a question, guess what? I'm on my phone. I got my own stuff to do, or I'm taking a nap. I'm executing the halt instruction. I'm taking a nap. Okay? So when you guys actually have something to ask me, you are going to raise an interrupt. Okay? You're going to come to me, tap my shoulder, and go like, hey, Tack, wake up. I got a question for you. That is an interrupt. Okay? Or you come to me and say, Tack, I know you're texting something that's really important, but I got a question. Can you answer my question? Okay? That is an interrupt. So what I will do is I'm going to put down my phone, or wake up from my nap, and I'll come to you, answer your question. I will surface the interrupt, okay, so to speak. I will surface the interrupt. So whatever the interrupt is, okay, if it's a keyboard thing, I will grab the key code, put it into a buffer, process it, and send it to whatever process is waiting for the key code. If it's a packet from the network interface card from the NIC, I'm going to look at the packet and go like, is that a part of a larger construct? Okay, you put it into the network protocol processing subroutine, okay, and say, okay, process this, okay. If it's your mouse movement, every time you move your mouse, if you see your mouse cursor moving, every single time you touch your mouse, it's generating an event. And it's basically waking up the processor and go like, hey, the mouse position just changed. Do something about it, okay. So the operating system, or I should say the GUI, the graphical user interface, will say, oh, okay, it moved by how much? Okay, in this direction, in the X direction by 20 pixels, in the Y direction it changed by 12 pixels. So then the GUI would basically look at that information and go like, okay, I'm going to move the cursor on screen by a ratio of that, depending on how you set up the sensitivity of your mouse and acceleration and stuff like that, but it will do whatever logic is needed, okay? And then what happens after that? after the source of the interrupt is addressed, the interrupt is surfaced, I answer your question. Okay, what am I going to do in the lab? I get back to my nap, right? I get back to my texting. I get back to my reading my email. So to surface an interrupt, the processor is going to go back to what it was interrupted with and continue with that. If it was executing the halt instruction, it gets back to sleep, take a nap. If it was updating Windows and whatnot, it gets back to the update of Windows. Is that making any sense so far? Just conceptually. Okay. What is that reminding you of? There's a
The address of what the process you were doing.
yep.
So when you change it on purpose, if you don't change it back, then you just crashed.
Well, you're doing something a little bit worse than consistently crashing it. Okay. So what's happening, or what the interrupt mechanism needs, is the stack that you are using in order for the interrupt mechanism to remember where to get back to. In other words, an interrupt, a hardware interrupt, is almost equivalent to a hardware on your PC calling a subroutine. Okay, let me say that one more time, because this is a concept that will come back to you when you're taking operating system at a 4-year university. A hardware interrupt is almost like a hardware device. Your USB controller, your NIC, your keyboard controller, okay, your sound card or whatever, is calling, the hardware itself is calling a subroutine. It goes through almost exactly the same mechanism to call a subroutine, which means the first thing it needs to do is to say, who am I interrupting? At what point am I interrupting? Let's save that address on the stack so that the interrupt surface routine, which is basically a subroutine kind of special, but it is still a subroutine, knows that when it's done surfacing the interrupt, it knows where to get back to. Is that concept okay? And where do you think that return address is stored? On the stack. And when do you think an interrupt can occur?
Anytime.
Anytime between two instructions of your program. Let me give you an example. So we're going to take our own example here. So that means an interrupt can occur between any two instructions, between these two, between these two, between these two, and so on. And you have no idea it's going to happen. It is called asynchronous because it is not, or it's not coordinated with the software. Okay, if you think about it, it makes sense. Okay, how can your program possibly know at which moment you're going to press a key on the keyboard and require the quote-unquote calling of the subroutine to process a key code? There's no way to predict it. So an interrupt can occur between any two instructions. So that means if you adjust the stack pointer in order to get back to an earlier location because you want to access a variable, okay, so let's emulate that effect here. And I spent exactly 10 minutes to do it. It's creepy because usually I don't do that. So if I use increment d to get back to x, okay, because it's convenient. Oh, d is almost there. I just need to add 1 to it. Okay, so let me finish this code first. Okay, so I'll increment d, ld, a, d. Okay, so the a has the value of x. Okay, okay, and with this instruction, the intention, okay, the intention is d equals to the address of x after the increment. With this instruction, a is basically the same as the parameter x. And then I go like, well, I know, I'm not supposed to do this. I'm going to decrement d so that, d is pointing to the return address. It is the address of the return address. So you might think that, hey, this is all cool. I mess around with d, but I restore the value of d. But then when you think about when an interrupt can happen, then it's not really that great anymore. Because an interrupt can happen right between these two instructions. Or, worse yet, between these two instructions. So let's think about it. What happens when the interrupt happens between these two instructions? Which means you successfully, did the LDAD instruction. Actually, I think between the other two instructions is more damaging in this particular case because we are only reading, we are not writing to it. So between these two is probably better. Okay. So let's say an interrupt happens between these two instructions. Is that okay? So you perform the increment D just fine. That's before the interrupt occurs. And then right after increment D and before load A with whatever D points to, the interrupt occurs. Okay? And tell me again, what is the first thing an interrupt mechanism wants to do? Save the return address, right? And it's going to use your own stack. Using the same standard, it's going to use register D to store the return address. Where do you think it's going to store it to?
Right over the old return address.
It's going to overwrite not the return address. It's going to overwrite your local your parameter x. Because after the increment, D now points to the address. Excuse me. Let me say that one more time. D is the address of x after the increment instruction. So if an interrupt occurs at this point, it's going to overwrite whatever is below it. Okay, you're correct. So it's going to overwrite the return address, which is right below that. So you would think nothing happens to my parameter. It's all cool. When you return from this subroutine, it's not going to return to main. It's going to return to this point because this is where the interrupt occurred. So the stack is quote unquote corrupted. It is overwritten in a way that it's not supposed to. Are we kind of getting that picture or not? Sort of. If you want to, yeah, go ahead.
The interrupt is just like a subroutine call. Anytime it's called, it touches the stack, so it just destroys all the work.
Yes, and you have no idea between which two instructions the interrupt is going to occur. So you cannot just say, I guess it's not going to happen from here to here. Nope, you have no idea when it's going to happen. It will happen whenever it happens. Okay? So are we getting the idea or not? Because I got more analogies for you guys to kind of grasp that idea. Yes? No? Okay. Do you guys want a Doctor Who explanation of this?
Sure. Wiggly wobbly ball of wiggly wobbly stuff.
Well, it turns out that that particular doctor did encounter this particular alien. It's the weeping angel. So the weeping angel example is really kind of cool because the weeping angel is an alien. But if you're observing the alien, it cannot do a single thing. It is a schedule. Okay? The moment you blink or you look away, the alien will do its thing and get closer to you. Is that okay? It is extremely creepy. It's one of the most creepy aliens of the Doctor Who. So kind of imagine that when you execute the instruction, you're looking at the angel. It's like, you're not, nothing happens. Okay, I'm doing my thing. I'm looking at you. Cool, nothing happens. In the transition from one instruction to the next, you're blinking. When you close your eye, okay, that is when the alien can do its stuff. So you open your eye again, and then suddenly the angel is now closer to you. Okay? So if you think about the weeping angel can do things between every instruction, and you are the person who's trying to execute this program, then you can kind of think about what is going to happen here. Because the weeping angel, in this case, says, I have legitimate right to the stack pointer. Okay? Because by agreement, anything below what the stack pointer points to is unallocated, it's free for me to use. That is the agreement, and that is the problem. Because once you increment the stack pointer, you are basically saying, oh, you know what, below this point, it's free, you can use it. And the weeping angel comes in and go like, okay, since that's the agreement, I'm going to assume, at this point, between these two instructions, I'm going to assume the stack pointer, or whatever is below the stack pointer right now, is free for me to use. But as it turns out, it is something that you still need It is your own return address. So that the interrupt does not know that, oh, I still need that. Because the agreement is anything below what the stack pointer points to is free, is available. Is that okay?
Gremlins.
Weeping angels. Weeping angels or meeping angels. So now you're making me to look this up.
Why don't you just get something an animal that doesn't blink like a mole rat, and then just tie it up in front of it?
Or any fish. Or any fish, if you think about it.
Just put a fish in front of it, and then it would never be able to move. And then break it with a sledgehammer.
Okay, so for those of you who like to watch, Doctor Who, you want to rewatch the Weeping Angel episodes because it really has to do with interrupts. And if once you look this up, you can also look up Meeping Angels,
And how does it discern between the
which is even more creepy. The
what if it's like an
Meeping.
insect that just flies near it, and then it has like that?
Oh, that's okay.
Flies in the room, it's all of a sudden immobilized.
Okay. Oh, it's searching. There you go. There's your Meeping Angel from the Muppets. Yep. The Meeping Angel. Some people say the Meeping Angel is more creepy than the Weeping Angel. I would agree. I would agree. All right. So this is not a good way to do it. So if you cannot change register D up to get something back, what are you gonna do?
Go all the way around again?
Make a copy of it and then use another register to get this job done. Okay, so instead of doing this, what we will do is we're going to say CPR. Okay, we're going to copy register D to, I just use register C for this purpose. You can use any of the registers. So after this instruction, okay, so after each instruction, I'm going to tell you what is the result of this. So after this, C now becomes the address of the return address. Now, I know it sounds really convoluted. It is the address of the return address. The content of the location pointed by C is the return address that we have to use later on. So right now, we don't need to use it, but we don't want to lose it either. And that's the reason why we don't want to increment the stack pointer. Register C is free for anyone to use, okay? And there's no agreement. The only agreement is the interrupt surface routine. If it uses register C, it has to restore it. It's kind of like the Weeping Angel has an agreement with you. It's like if the Weeping Angel uses your coffee mug, it has to clean it. If it drinks a coffee, it has to refill it. So by the time you look at the Weeping Angel again, your coffee is not changed. It has the same level, tastes exactly the same, has the same amount of sugar, has the same amount of creamer, because the Weeping Angel is responsible to restore whatever it drank or whatever it changed back to the original state when it is the other registers. Okay?
Just not the stack pointer.
The stack pointer, it restores it too. You have no idea that the interrupt actually occurred. Okay? So,
It doesn't restore the data that was stored, though. It just stores the pointer.
right. Now, if you look below where the stack pointer points to, you might notice that something has changed. But that's okay, because the agreement is anywhere below where the stack pointer points to is available. So what if it changes? It's okay. It is the locations that are either pointed to by the stack pointer or above what it points to that is not supposed to be changed by the interrupt surface routine. But whatever is below the stack pointer is free, is available. Okay, so the next instruction is I can now increment C, not D, okay, because register C is supposed to be restored by the ISR if if an interrupt does happen. So by incrementing it, C now becomes the address of X, okay, parameter X. Oh, we do need that, right? We need register X so that we can implement X plus Y, okay, so that's useful. So we're going to put it somewhere, okay? We'll put it into register B. So B, register B is now parameter X. Let me just pause here to make sure that you guys can actually differentiate between the address of the parameter versus the value of the parameter. Is that okay? Cool? Yes? Okay. I'll get back to this point a little bit later because there's something about C and C++ versus assembly that kind of makes this kind of interesting. If I increment C one more time, what do you think C becomes? The address of Y. Very good, because you can see the map here. Y is just 1 byte on top of X. So if I increment C, it now becomes the address of Y. And I need that too. Okay, we'll put it into register A. So now register A is the value of parameter Y. So now we have put the two values that I'm supposed to add into two different registers, which is what we need for the add instruction to execute. Because in the toy processor, the only thing we can do with add is whatever we're adding, they have to be in registers. So the next instruction is really just an add instruction, and I specifically want to add B to A. Okay, so A becomes A plus B, which is X plus Y, which is the value of parameter X plus the value of parameter Y. Is that okay? And why do you think I chose add AB and not add BA? What is so special about A? It is the agreed return value register. Very good. Okay, so it is supposed to be the return value register. I don't have to do a single thing after this point to specify the return value because the register that I store the sum is the return value register. So at this point, I have nothing else to do except to finish up the return mechanism. The return value is specified, but I need to do the actual return back to the caller. Now, this is the other place where some confusion can happen, because in C and C++, the return statement is doing both. It is both specifying the return value and also returning back to the caller. But in assembly, those are two kind of distinct operations. You specify the return value by putting something into register A, but that by itself return to the caller. You have another 3 instructions to execute in order to return to the caller. All right. All this time, what is D pointing to? D is always the address of the return address, right? That's convenient because I can now say load B with whatever D is pointing to. So B is now what? Is it the address of the return address or is it the return address itself? It's the return address itself because we just dereferenced the address of the return address. I know it sounds really convoluted, but that's exactly what is happening. Okay, so B is the return address, which is cool. We'll use it later. But before we use it, we're going to do a increment D so that we can deallocate the return address or the byte used by the return address, because I don't need it anymore. I have now put it into a register. We'll use it in the next instruction, but I don't need it on the stack anymore. So if an interrupt is to occur at this point after the increment D, doesn't hurt me at all because that location is of no value to me at this point.
Because we're cleaning it up so we can go home.
Yep, so we can clean up so we can go home and have dinner. Yes. So JMPB is going home. So there are several distinct things that is happening here since you talked about going home and have lunch, have dinner and whatnot. So LDB in parentheses D is retrieving the map so that you know where to go home. Okay, you're retrieving the GPS location of home. Increment D is destroying the map because you don't need that anymore, or destroying the coordinate. Okay, kind of like Mission Impossible. Once you listen to a mission, it self-destructs. Okay, so we're now destroying, the things because we have used it already. JMPB is to say, oh, I remember the coordinates. I'm just going to go there now. Is that okay? Are we kind of differentiating what each instruction is doing in the mechanism of returning to the caller? Is that okay? Cool? Okay. So I think we got the whole program. We got the main subroutine, which is the caller, which also has a local variable, which is initialized by this code. We have the subroutine, which is f itself. Seems like it's fully implemented. And I remember I said a little bit earlier that I have something to kind of point out. In C, it is easy to see that, oh, I'm referring to the value of parameter x. I'm referring to the value of parameter y. In C, if you want to get to the address, you have to specify ampersand. So it gives people a false impression that it takes more work to get to the address of something than to get to the content. Does that make any sense? Because you have to specifically say, oh, I don't need the value of this variable. I need the address of ampersand something, right? But in assembly programming, you will start to see that, oh, that is really not the case. Because in order to get to the value of something, guess what? You always have to compute the address of that something first. So in assembly, the first thing you need is the address of a variable. From the address, now you can choose to dereference to get to the value of the variable. You always get to the address first. Then you can choose, do I just need the address? Am I passing the address? Or am I doing some calculation with the address? Or do I actually need the value at the address? It's getting the value that is the quote-unquote extra work. It is not getting the address that is the extra work. So that is kind of interesting, and I want to point it out because it is counterintuitive. Because we are so used to C programming. Okay, we keep thinking, oh, we get to the value first. It takes extra work to get to the address. It is exactly the opposite in assembly language programming. Is that okay? All right. So I think we're done with this program. So I'm going to do a Control A, Control C, and go to my assembler. Okay, so let's find the assembler. And shared, processor, assembler, and then we'll paste the code. There. Hopefully I didn't make any error here, so we'll wait for the error checking. Okay, looks okay to me. Then we go to RAM file.
Did you make this yourself?
Yes.
Oh my god.
Well, I wouldn't say this is half the fun. It is 99% of the fun.
It's solving a puzzle.
It's putting something together that works.
It's like making a puzzle and solving.
Well, from your perspective, I'm making a puzzle, but from my perspective, I'm making a tool that makes puzzles, which by itself can be considered a puzzle too. I'm solving a puzzle to make a machine that makes puzzles.
The assembler I can understand.
A second order puzzle.
There you go. Puzzle within a puzzle.
Having it check for errors within the code though, that must be really hard.
Well, I don't check for everything. Like you can define a label twice, it doesn't quite catch that. So maybe at some point I'll add the code to do it.
Oh, that changes my entire opinion of it then. Basically no effort whatsoever.
And we want to run the Logisim, get the processor up, load it in, and then we'll talk about how to test the program. Because there's no C in, there's no C out. GDB doesn't even work here, right? So how do we check it? There are ways to check. Sorry?
Logging it.
You can log it. With something like this, it depends on how confident you feel about your code. Okay, so I'm going to do two ways to do it. I'm going to go for a two-prong approach. The two-prong approach, okay, so let's load the program in first. Okay, so we're going to do a load image to the temp folder. It's called simple.csv. Program's in, but I'm not going to run the program just yet because I want to set up some logging. So you go to simulate, go to logging, and then we'll start to pick things that we want to log. The first thing we want to log is going to be the program counter. This is almost the default thing that you have to log when you're debugging a program. And we almost always want to change it to either hexadecimal or decimal. I personally prefer hexadecimal. The reason why we always have to track the program counter is we want to find out when which instruction is responsible for this register changing or that memory location changing. The program counter is your only clue of which instruction is responsible for that operation. Okay, so you always want to track the program counter. It's almost like, if you're looking into a GPS application, tracking the program counter is tracking your location. So if you want to be able to retrace your route, how did I get here? Okay, you have to track the program counter because it leaves behind a trail of, oh, you got here, you got here, you got here, you got here. This is how you fell off the cliff, and this is where you got waves, and this is where you got picked up again by the Coast Guard, and this is where you end up with hospitalization, and so on and so forth. So your GPS is tracking all of that stuff. You want to track your locations. That's your program counter. Another thing that you want to track is register D. Do not track this one. This is the output pin called D, which is the data bus. So this is not what you want to track. You want to go to the register bank right here and track the register D here. So once again, well, that's raining. Okay, change it to base 16. Now register D is very significant because it is your stack pointer. Now there are two ways to kind of find out what memory locations you need to track. You can either analyze the program and say, okay, the main program here needs 1 byte for the local variable. To call the subroutine, we need 2 bytes for the 2 arguments, 1 more byte for the return address. So the entire program will modify up to 4 locations from the end of the stack. So you can figure that out by reasoning, or you can track how register D is changing, and then look at the log and find out what range of memory locations you really should be tracking. Okay, so that's why register D is particularly useful or important. You can also track locations in RAM. So when you double click on RAM, it shows you all 256 locations. The first few locations, they're just the code we're not that interested in. It is the last few locations that are interesting, that is really useful. So if you think you might be underestimating how much RAM locations are actually used on the stack, you can always track a few more. Okay, it doesn't hurt. Okay, it just makes your trace a little bit wider, but not necessarily longer. So I can always just kind of overestimate and track more locations in RAM than I really need to. And change each one to base 16, like so, like so. Yeah, it doesn't do that. I don't think we can select multiple and then change all of them. But it's open source. If you want to change the source code and so that you can batch change the radix, it can be done.
There goes my weekend.
But it's fun. It's fun stuff. Okay, so I'm going to track it and put it into what we call a TSV, or a tab separated value file, so I can import it into a spreadsheet if I want to. So now we're all set up. Now, before we go actually executing the program in full speed, when you are writing your program and you're suspecting, I don't think the program is doing something right here. Okay, one thing you can do to debug your program is to go to the source code first. Okay, I always like to go to the source code to change that first. So if you suspect, okay, I think everything is done correctly here, but if you suspect that something is not right, okay, that A and B are not the values of the parameters, something is wrong, either the stack pointer is not initialized correctly, or C is kind of messed up, I messed up the calculation, you can put a halt instruction here, which is not what you want to turn in, because your program is not supposed to halt inside the subroutine. But when you're debugging your program will basically stop right there. So you can then look at the RAM, you can look at register D, you can look at register Z and everything to say, okay, is everything the way they're supposed to be? If they're not, then you can move the halt instruction back a little bit until you find out what's wrong with your program. So the halt instruction can be used as a very crude way of debugging your program. It is not as good as a trace, but it's convenient. Okay, especially when your program has loops and recursion and stuff like that, this might actually be a better way to debug your program. Okay, so getting back to the simulator, everything is ready. So let's go ahead and do a control K, start the clocking at full speed. It's done. Control K again to stop clocking. So the first thing I would do is being optimistic and go to the memory locations here and go like, well, did I get a job done? So which location again is my local variable n on the stack? Location 255, which is location FF in hexadecimal, right? Is that a 5? Yep, we have a 0, 5 here. So I'm fairly confident the program is working correctly. But I look at the other locations and go like, hey, there are some values over there. Can I explain that? Now, in this case, I can look up the entire stack after the stack pointer has retracted entirely, because there's no interrupt mechanism in this processor. So that's why I can do a post analysis like that. If your processor has interrupts, then you cannot rely on the content on the stack at this point, because interrupts could have happened and mess around with the stack content. Is that making any sense? Okay. But since I do not have an interrupt mechanism, I can do this. So now the question is, what is this 0, 3 doing here on the stack? That's my second argument to function f. What is this 0, 2 doing here on the stack? That's my first argument to function f. I can see that 1, 0 is here. What is that? It's a return address. Okay, but a return address should have a particular value, right? I should be able to find out location 1, 0 and see if it is corresponding to the label of the return address, right? So I need to double check now. Because just suspecting that is the case is not enough. Okay, so I want to go to assemble. I go to main return main return from f, okay, as a label, and it has a value of 16 in decimal or 10 in hexadecimal. That explains the 0 on the stack. Okay, so now basically get a stack that has changed. Let's check out the TSV file and see what it has logged. Okay, so we go to I'm going to import it into a spreadsheet. Okay, I think that might be a better way to do it. So I'm going to do make a new spreadsheet. Unfortunately, it doesn't automatically create a new spreadsheet inside the share folder, which I think would be the better way to do it. So I want to do an import from the TSV file. So we're going to do an upload.
I think if you were in your shared folder and created a new one, it would be.
Oh, okay. Yeah, but that spreadsheet itself is in the share folder already. So you would imagine that, if you say new in a spreadsheet that is already in a share folder, it would use the same folder. I don't think that is the case, unfortunately. Okay, so we open the TSV file, and it will give you options. Okay, so there are several things that are kind of important. The first one is do not convert text to numbers, because that's going to mess up all the leading zeros, and it will convert things that look like a decimal number, but hexadecimal numbers it doesn't know what to do with. So I would turn off convert text to numbers and dates. The rest, I think we're pretty safe to use it. Replace spreadsheet and all that stuff. So import data. And it looks like this. But you can basically see how the stack pointer is changing from 0, 0 to FF to FE and so on. You can also see the stack content changing later on. Okay, so starting with this part here, we should see some changes on the stack. And I'm not seeing it. Oh, okay, so it starts to change here. The reason why we're not seeing it FF getting changed is because when we decrement the stack pointer to FF, we're just allocating the space. So location FF itself is not changed. Then we decrement the stack pointer to FE. So when you see the transition from FF to FE, that's the decrement D doing its job. Okay? And then a few instructions or a few clocks after that, it starts to change location FE to 03, which is our second argument. And then we decrement the stack pointer to FD. After the decrement, we see that the location FD is now changed to 02, which is our first argument to the subroutine. And all this time, the program counter is tracked. And you can definitely tell when it started to execute the subroutine is when you see a big jump of the program counter going from, let's see here, when the program counter changed, that is not obvious here, is it? Okay, from here to here. Okay, so when the program counter changed from 0F in hexadecimal to 15 in hexadecimal, that's when the JMPI instruction executed. Now you can always double check, okay? You can always double check and find out, is the label F the same as 15 in hexadecimal? It should be, because that's the entry point of the subroutine. Is that okay? So that means a particular slice of time is important, is this one here. This is a snapshot of what is on the stack, what the stack pointer is pointing to at the entry point of the subroutine. That is important because the stack pointer is pointing to location FC, which is this location. So the stack pointer is pointing to the return address. 1 byte on top of that is our first parameter. 1 byte on top of that is my second parameter. Now, we know this is local variable end of main, but the subroutine is not supposed to have access to it. Is that okay? So this is how, how we start to getting into subroutines, getting into parameters, and getting into function calls. Your lab activity tonight is not going to be due tonight because it involves the writing of a subroutine, so it's due in a week instead. But you should start to do it as much as you can because the first chunk of questions, they're all trying to explain the same thing that I just explained today, so you're getting a double exposure to the concepts, but in a slightly different program, a different sample program. The last question is asking you to write the subroutine code itself for swapping two integers. But the explanation of how to do it is in the first chunk of questions. So only the last one should be the one that you won't finish tonight. The rest you should be able to finish tonight. You can also do several attempts because you want to double check and make sure that you answer the first chunk of questions correctly. It will take the highest score anyway. So you should retry it until you get all the first few questions correct, except for the very last one where you have to turn in something and I have to grade it manually. So is that okay for tonight's activity? Okay, so I'm going to stop the recorder and then we'll head out to the lab. You guys can take a short break and then we'll get this program up and running.